So welcome everyone to our last Physics 157 lecture recap. And today we are going to continue talking about waves, and we'll continue on in our discussion of standing waves and their relation to musical instruments. And then towards the end of the lecture, I'll talk about one final new topic and a really interesting application of that. So just to remind you about what we were talking about last time, there was this principle of superposition that said that if you want to figure out the net displacement from multiple waves propagating in the same medium, then all you have to do is look at the displacement that you would have at any time for each of the waves individually, and then you just add up the displacements. So another way of saying that is that the waves add without disturbing each other. Mathematically speaking, this is related to a property of the wave equation that you may have heard about in my bonus video. So the equation that governs the propagation of waves on strings and in other media. So this equation has the property that if you have one solution, d1 of x and t, that's sort of an allowed physical wave. And if you have another solution, d2 of x and t, well, then there's a third solution, which is just the sum of those two solutions. Okay, so that says that the wave equation is what we call a linear equation. So we had an application of that, which was that if you think about a right moving wave and a left moving wave, and they have the same amplitude and the same wavelength. So the superposition says that you can add those up and that the result is an allowed wave for your system. And so if you do that, then what you end up with is this standing wave function here. And so instead of traveling to the right or to the left, what it does is it just kind of hangs out in one location. So at specific places that we call nodes, the wave is always zero. The displacement is always zero. So those are where this k times x is equal to pi over 2 or minus pi over 2 or plus or minus 3 pi over 2. And then in between, you have what we call antinodes. And these are places where the cosine function here is plus or minus 1. And so everywhere along the wave, then the thing just oscillates up and down. And so if you're at a node, nothing happens. If you're at an antinode, then you go from the maximum amplitude to negative of that. And an example of where these standing waves are relevant would be the situation where you have a wave, but the ends of the string are fixed at some location. So for example, when you have a guitar string, then your wave is required to be zero at those two ends. And you can see that having one of these standing waves, mathematically, that satisfies the constraint. But you have various options. And so we saw that for a guitar string, you could have a wave that oscillates like this with only the nodes at the two ends. But you could also have a wave with a shorter wavelength where it's oscillating like this. And then you also have one node in the middle, or you could have two nodes in the middle, and so forth. So depending on the length of your string, then you get these various allowed wavelengths, 2L, L, 2L over 3, 2L over 4, and so forth. And then in terms of the frequency, which for a musical instrument determines the sound that we end up hearing, we can go from the wavelength to the frequency using our standard formula for waves, which is that the frequency is the velocity over the wavelength. Okay, and we talked about how the velocity was just a property of, in this case, the tension and the mass density of the string. So it's fixed for all of these different wavelengths. And so you can have, for a single guitar string, different possible ways of vibrating, and the lowest frequency, which corresponds to the longest wavelength, that's what we call the fundamental frequency for that guitar string. And then all of these other ones are going to be multiples of that frequency. We call those harmonics of that fundamental frequency. Now, it's basically the same thing for other kinds of instruments, such as a wind instrument. So if you have an instrument which would be a tube where like something like a trumpet, and then you blow on one end. So it's closed at that end, but open at the other end. And then the waves in that tube, they would have a node at the closed end and an antinode at the open end. Okay. There, it's not a transverse oscillation like you would have with a guitar string. It's actually a longitudinal wave because it's just sound traveling through the air. And so you have, that's what the graph represents. It's like the longitudinal vibrations of the air molecules. And so you have these various possibilities. But again, if you demand that there's a node here and an antinode at the other end, at the open end, then you're going to have this situation where you've got a quarter wavelength fitting in your tube, or you can have a shorter wavelength here where 3/4 of the wavelength fits in, or you could have this situation. So I can try to demonstrate that. I'm not really a trumpet player. My son plays the trumpet. So I could try to demonstrate that though with the trumpet. So what I'm going to do is just leave the trumpet. I won't use any of the buttons. I will just play the trumpet, and so that's going to be some fixed length of tube, but I'll try to show you how you can get different notes. And so let's see if I can do that. I'll turn the microphone down so we don't overload it. All right, so as promised, I'm a very poor trumpet player, but you could hear that I was playing different notes, and these are basically the different harmonics inside the trumpet. So it's the same length of tube, but we can have different ways that the air can vibrate there. Okay. So I gave you this example at the end of last class. It was tied into our second homework assignment of the term. We had this very special instrument with a platinum wire stretched on a gold frame. The tension was 800 newtons. And I wanted to figure out what did that actually sound like at the start of the very serious skipping and clapping race. And so I want you to just think about that for a little bit. Use the information that I've provided. So I've actually got given you the mass density. Given the wire diameter and the density of platinum, you can figure out this mass per unit length. So I've already done that, but you can think about how would I actually derive that from this information? And then also, given all this information, what is the frequency of that note that started the very serious skipping and clapping race? Okay, so I will give you a minute to think about that, and then we'll go through it. Okay, so let's talk about this. First, let's talk about how we would calculate the mass per unit length of this wire. And so the easiest way to think about that is so that's like how much mass per meter. So what I want to do is I want to just think about a meter of wire. I'm going to calculate how much mass that would be, and then that will be our mass per meter. And so that will be the mu that we need to plug into our formula for velocity. And so this is pretty simple. Once I think about that meter of wire, it's basically just a solid cylinder. And to find the volume first, I multiply the length, which is 1 meter, by the area, which is pi r squared. The radius is half the diameter here. And so then that gives me the volume. And then I multiply that by the density of platinum. And when you do all of that, you end up with this value, 0.0168 kilograms. So that's the weight of a platinum wire here of length 1 meter. And so then the mass per unit length for any length of wire would be 0.0168 kilograms per meter. And so that's how I got to the mu. Now I want to calculate this frequency for the note that I would hear if I pluck this very special, what was it called? The most perfect plucking instrument. Okay, so we want to look at these possible patterns, and the one that you will hear corresponds to the longest wavelength or the lowest frequency. Okay, so that would correspond to this method of vibration where the wavelength is twice the length of the string. So in this case, we want to use a wavelength of 2 meters. And in order to figure out the frequency, we just then use the frequency equals the velocity over the wavelength. Okay, and velocity, we had this formula last time, which is the tension, 800 newtons, divided by the mass density. So you work out the velocity of waves on that string. You use the longest possible wavelength, which is what we will hear as the frequency, and then we end up getting a frequency of 109 hertz. And so it just so happens that 109 hertz is pretty much the frequency of the second string on a properly tuned guitar. And so I will now play that for you. So this is what it sounded like at the beginning of the very serious skipping and hopping race. 3, 2, 1. Okay. All right, so continuing on with this idea of understanding the sounds from musical instruments, I wanted to ask an interesting question here, which is, why do different musical instruments sound different to us if they're playing the same note? So like that note I just played on the guitar, 109 hertz. I could play the same note on a saxophone or on a brass instrument or on a cello, and they would all sound different, even though they're the same note. And we would normally say, well, that note corresponds to that particular frequency. So why is it these instruments sound different? So the reason is that when I play a note on a musical instrument, it is not just the fundamental frequency that we're hearing. So let's take the example of the guitar string. So you could pluck the string, and I showed you the other day how you could pluck it very gently in the middle and mostly get the fundamental frequency. Or you could pluck it, or you could put your finger in the middle and pluck it over here and mostly get this second harmonic. Or I could try to arrange so it's mostly vibrating in the way that I've shown here with the third harmonic. But if you just randomly pluck it, it's going to be a combination of all of those different ways of vibrating. So a superposition of these different kinds of standing waves. And the same is true for a saxophone or for a trumpet or whatever your instrument. You're generally hearing the fundamental frequency plus various combinations of harmonics, which would be multiples of that frequency. And so the difference then is how much of these harmonics do you have relative to the fundamental? So in order to display that information, I could describe a particular musical note played by a saxophone or a trumpet by a spectrum graph, which is very, very similar to the kind of spectrum graphs that we used for light. Okay, so we could plot on the horizontal axis, I could plot frequency. I could have also used wavelength, but I'll use frequency. And on the vertical axis, it's like amplitude or power. So one of those things. And so what you can see here is that if I say play a note on the trumpet, then we're going to get a certain amount of that first harmonic. So a certain power at that frequency, and then a certain power at, say, double that frequency, and a certain power at triple the fundamental frequency. And there are going to be different amplitudes for each one of those. So I have a demonstration that illustrates this. So using what's called a spectrogram, And this is actually something that I'd encourage you to play around with. It's basically just, you can get these free spectrum analyzer graphs for Mac or Windows. And so let me just turn on the sound for you all so that you can hear the video. Okay, so we should be ready to go there with our, maybe. There it is. Okay, so we should be ready to go with this video. Let's try it. All right, so welcome. What we have here is a spectrum analyzer. And so what it's doing is it's taking this sound from my microphone and it's showing you a spectrum graph, just like the ones we had for light, but this is showing you how much power there is at various frequencies of sound. And so what I want to show you is what a musical note looks like. So I'll start by whistling a note. Okay, and so you can see that that was pretty much all at one frequency. And if I whistle at different notes, you'll see them peaked at different frequencies. Okay, so with a musical instrument, then what you find is that you have the fundamental frequency, the frequency that you hear, but then also it's blended in with a whole bunch of higher harmonics, so multiples of that frequency. And that combination of frequencies is what makes the note actually sound good. And so I'm going to turn my mic down and play something on the saxophone So there we go. That was a nice physicsy song, the force theme. Okay, so, oops, where'd my slides go? There we go. Yeah, I thought of that when I was a child in school. Occasionally there would be musicians that would come, and I remember that everyone would always ask these musicians to play the Star Wars theme. So in this video, oops, we're going to continue thinking about multi-part quantum systems. Wow. I'm going to introduce the idea. Okay, we don't want to think about silly autoplay. Okay, so we're not going to talk about multi-part quantum systems or entanglement today, but I will continue with my story. Right, it was sort of the original Star Wars generation, and yeah, the Star Wars theme was the coolest thing you could possibly play on a musical instrument. I think that's why I thought of it. It was the main theme back then that everyone liked, but I chose the Force theme there because that has a nice physicsy angle to it. So I want to talk now about kind of our last topic, the last concept of this course, and it's related to the superposition principle. And so it's the idea of interference of waves, which, as I'll explain, is kind of a bad name because the superposition principle says that waves don't really interfere with each other in the usual sense of it. They kind of pass right through, but we still call this interference. So you probably heard about this at some point in high school or in another context. And the idea is that we're going to consider waves from two different sources and think about the net displacement at some point, which according to the superposition principle would be the sum of the displacements from the two individual waves. So let's think about the possibilities for that. And I want to imagine that, let's say we have two speakers and each of them is playing a single frequency. So we have a single wavelength. And so the displacement at this point P would be a nice sinusoidal function like that. And then we take the other wave and we add it. And in this case, the point P is at the same distance between P and 1 and P and 2. And so you're basically getting exactly the same signal. You're getting the same displacement at this point P from speaker number 1 as you are from speaker number 2. And so those things just add up nicely and give you a displacement which is twice the amplitude as the displacement you'd get from either one of the speakers. And so this is what we call constructive interference, because the two waves are just adding up constructively. In contrast, if we think about a point Q here at a slightly different location, then what you see is that the wave from speaker number 1 has to travel a little bit further, and the wave from speaker number 2 has to travel a little bit less. And so if the two waves were in phase coming out of the speakers, then they might end up being out of phase when you go to the location Q here. Okay, and in that case, what can happen is that even though you have these two sound waves and they're both meeting at Q, what can happen is that they cancel each other out or partly cancel each other out. And so when you're at Q and you turn on speaker number 2, it actually gets quieter. So destructive interference is something where if you're at the right location, then the combined signal from these two sources would actually have a smaller amplitude than the individual signals themselves. And so this is what we call destructive interference. This is the principle behind noise canceling headphones. They produce a second sound that cancels out the sounds from around you. So I want to think a little bit more quantitatively about that and understand what distances should these speakers be at from our place where we're listening if I want to get constructive interference or if I want to get destructive interference. And it's easiest to think about everything happening in one dimension. So obviously, if the speakers are at the same location, then I'm going to get constructive interference because if assuming the speakers are in phase with each other, those waves will travel together and the wave displacement from one speaker will look just like the wave displacement from the other one, and so they'll add up. But now I can consider moving the blue speaker backward a little bit. And if I move it backward by exactly half a wavelength, and I take a picture of the waves at some time, then what you notice is that in that situation, the blue one is 180 degrees out of phase with the green one. And so everywhere along this path, if I add up the two waves to find the net displacement, then they're going to add to 0 or very close to 0. And so we would get destructive interference if the path length difference is lambda over 2. Now, if I move that blue speaker back a little bit more until it's a full wavelength separated from the green speaker, in this case, the two waves, as you can see, are in phase again. And you can continue the pattern. So you'll find that for a path length difference of lambda over 2, 3 lambda over 2, 5 lambda over 2, and so forth, we'll get destructive interference. If the path length difference is 0 or lambda or 2 lambda or 3 lambda, and so forth, you'll get constructive interference. So here's a relatively simple question to think about. I want to know if I play the same sound from these two speakers and it's in phase, what is the lowest frequency I could play so that I would get constructive interference at the point P? So take a minute to think about that, and then we'll talk about it. Okay, so let's do this question. So the first thing we want to realize is that there is a path length difference. Speaker number 1 is 12 meters away. Speaker number 2 is 13 meters away. And so we have a path length difference of 1 meter. And then we remember that constructive interference happens when the path difference is equal to 0 or lambda or 2 lambda. And so clearly 1 meter is not 0, so we can't have that. But what we could have is lambda equals 1 meter, or you could have 2 lambda equals 1 meter, so lambda equals 1/2 a meter, or you could have 3 lambda equals 1 meter, so lambda could be equal to 1/3 of a meter, and so forth. So for all of those possibilities, then you're going to get constructive interference. Now we want the lowest frequency for constructive interference. So we have to convert these wavelengths into frequencies. And we're going to use that f is equal to v over lambda, where v is the speed of sound, 340 meters per second. So to get the lowest possible frequency for constructive interference, I want to use the largest possible wavelength. That's 1 meter. So I get the frequency equals 340 meters per second divided by 1 meter, which equals 340 inverse seconds, or 340 hertz. So the answer is B, 340 hertz. Okay. So I wanted to show you an application of this constructive and destructive interference. It's a really cool technology called an interferometer. And to set the stage for this, I want to imagine that, for example, suppose you have a cooler, and suppose that out of the cooler you take a brick. Okay, so you take a cold brick, and now it's at room temperature. And what you'd like to do is figure out, as this brick heats up, is it actually changing size? Is it getting longer? If it's getting longer, how much longer does it get if the brick heats up by 1 degree or 2 degrees or 3 degrees? Okay, so obviously this connects with something we talked about very early on in the course. And now, using our knowledge of waves, we can understand how you would actually make that measurement. So the idea of an interferometer is that you take a source of light, usually a laser beam. So that's a source of light with a particular wavelength. And in this case, we're going to assume it's red light with a wavelength of 600 nanometers. And what I do is I split up the laser beam into 2 parts. And I'm going to send one part down a simple path that goes from the laser, from the splitter, right to a detector or a screen. But then the other part I've arranged to travel on this other path using mirrors here. I take the laser, I bounce it from one end of the brick to the other end of the brick, and then it bounces back, and then it goes into the detector. And so what we're going to do is just observe the combined signal of these 2 lasers at the detector. And the interesting thing is that as the brick changes its length, then we might go from a situation of constructive interference to destructive interference and back to constructive interference and so forth. So let's look at some data that we might get in such an experiment, and we'll try to interpret that. So we do this experiment, and we imagine the brick, say, heats up from 293 Kelvin to 294 Kelvin. So maybe it's already almost at room temperature, and it's heating up this 1 degree. And what we see on the screen here is a pattern which is bright, and then it dims, and then it gets brighter and dimmer and brighter. And it does that 1, 2, 3, 4 times over this 1 degree Kelvin that the brick is heating up. So I want you to think about now, using our understanding of when you have constructive versus destructive interference, by how much did the brick's length change between 293 and 294. Okay. So let's talk about it now. So what happens here when we go from this point where you have the maximum brightness to the next point where you have the maximum brightness? What it must mean is that the path length difference between path 2 and path 1 is some multiple of a wavelength. We don't know which multiple. It's some huge multiple, but we don't really care. What we care about is that it's just constructive interference. And then as the brick gets a little bit longer, you see that the path number 2, it gets longer as well. Okay, so if the brick got 100 nanometers longer, path 2 would get 200 nanometers longer. And so what must be happening here is that when we go from this peak to the next peak, path 2 must have got one whole wavelength longer, kind of like when we moved that speaker back one entire wavelength, and that went from constructive interference to constructive interference again. So we could conclude that going from this peak here to this peak here, the path length gets longer by 600 nanometers, and therefore the brick gets longer by 300 nanometers because the path length traverses the brick twice, going there and back. By this location, the path length must get longer by 1200 nanometers, here 1800 nanometers, and here 2400 nanometers. So going from 293 Kelvin to 294 Kelvin, the brick's length is going to change by 1200 nanometers. Okay, and so that's how we could explain this. The brick changes by 1200, so path number 2 gets longer by 2400. That's 4 wavelengths, and that's why it goes up and down 4 times. And so we could use that measurement to calculate the alpha value for brick. And so if you take delta L over L and then delta T, and suppose the brick is 20 centimeters long, then that ends up giving you 6 times 10 to the minus 6 inverse Kelvin. Okay. So we can use this property of waves and their constructive and destructive interference to make these extremely accurate measurements of changes in length. So to finish, I want to tell you a story that involves waves and it involves interferometers, and it's one of the most amazing things that's happened in physics in my lifetime. And so this is something to do with Einstein's theory of gravity. It's what's called general relativity. And as you probably have heard at some point, Einstein understood gravity as an interaction between matter or energy and space-time itself, which he understood to be a dynamical kind of medium. So in Einstein's theory, space is something that can bend and warp, and it does that under the influence of mass and energy. And one of the predictions of Einstein's theory of gravity is that because space-time is this thing that is dynamical and can be bent and warped, kind of like a rubber sheet or any other material, it can also have waves traveling along it. And so the way that you get these waves is you drive an oscillation. And for example, you could have an oscillating matter system like 2 stars orbiting one another. So in this oscillating matter system, that sort of causes the space around the stars to start rippling. And then there's a wave that is traveling outward. And it's not a wave of anything but just pure space. It's not light. It's not sound. It's just going through empty space. And it has to do with just the stretching and bending of space itself. And these waves are actually something that can carry energy away from one of these star systems. And so they're, they're real physical entities. And people for decades have been wanting to try to measure those waves directly. So to find direct experimental measurements that show the existence of the gravitational waves. And so we have to ask, how would you see such a gravitational wave? What does it mean for a gravitational wave to pass by you? What would you notice? And so because a gravitational wave has to do with the stretching and warping of space-time, the thing that you would notice if you have, say, two objects and a gravitational wave happen to pass by, what you'd notice is that the distance between the two objects would temporarily get shorter and then longer and then shorter and then longer. And it wouldn't be because the objects are moving. It would be because the space in between them is actually contracting and stretching and contracting and stretching. So the way to detect the passage of a gravitational wave is to look for these oscillations in the distance between stationary objects. So the people on an experiment called the Ligo Experiment, I think this is laser, this stands for interferometer, this is probably gravitational wave, and O is observatory. What they decided to do was build the world's greatest interferometer. And it was a giant interferometer. They actually built two of them in different parts of the Earth, as I'll explain shortly. And these things, instead of the distance of a brick from one end to the other of path number 2, this distance they made it to be 4 kilometers long. So this giant interferometer where the laser beam splits. But other than that, it's basically the same idea as for the interferometer that we discussed. And so what they were looking for is the passage of these gravitational waves. But the problem is that lots of things cause the distance to vary. And most of those things are just vibrations of object number 2 or object number 1, rather than space-time oscillating in between the two objects. So how can we distinguish a gravitational wave causing a slight change in the distance compared with maybe a truck driving by nearby on the highway? And so there's a couple of different ways. So the first thing is that they built 2 of these detectors. So one of them is in Washington State, and the other one I think is somewhere else far away in the United States. Now I think there's a third one. And so basically, if it's a gravitational wave, then you should see the same signal on both detectors. If it's a truck going by, you'll only see it on one of them. Okay, so you can compare. But still, you want to know precisely what you're looking for. And you have to decide, well, where are these gravitational wave signals likely to be coming from? And so it turns out that the strongest and most easy to interpret gravitational wave signals are signals produced when 2 black holes that are rotating around each other end up merging into a single black hole. So these cosmic collisions of gigantic black holes will produce very large gravitational wave signals, severe distortions of space and time near that collision. And then they travel through the universe. And like light waves, their intensity decreases. So the amplitude of the gravitational wave gets smaller and smaller and smaller as you go further and further away from that collision. So there was this one very special collision that happened in a galaxy far, far away, about 1.4 billion years ago, where a couple of black holes that were something like 30 times the mass of the sun collided and merged, producing a huge gravitational wave that started traveling outwards in all directions. In particular, some of it was traveling towards the Earth. And 1.4 billion years later, on September the 14th, 2015, this gravitational wave, it hit the 2 different gravitational wave detectors built by the LIGO experiment. And they were all ready to know what to look for because people on the theoretical end of this project had done various supercomputer simulations to predict exactly what sort of displacement function to expect from a gravitational wave that would come from the merger of 2 black holes. And they tried all of the different possible masses. And so what happened on September 14th, 2015 is that this tiny signal was detected at both interferometers with the same exact wave shape. So this is like a wave pulse with this shape. And it was exactly or almost exactly matching the theoretical predictions of the wave shape that you would get if a 36 solar mass black hole collided and merged with a 29 solar mass black hole. So you can see here the black line is the theoretical prediction for what that should look like. The orange line is what they saw at the Ligo experiment in a place called Hanford. The blue line is what they saw at the Ligo experiment in a place called Livingston. Okay, and so seeing how well this matched the theoretical predictions and seeing the exact same signal at the same time at these two detectors thousands of kilometers away gave the scientists confidence that they had actually indeed observed gravitational waves from colliding black holes. Now, the last thing I want to point out is the y-axis here. So how big was this signal? How much change in distance did you have in this 4-kilometer long path length? And so you notice our old friend strain, which is delta L over L. And you see that the scale of this thing is 10 to the minus 21. So if delta L over L is 10 to the minus 21, that means the change in the distance, the change in this 4-kilometer distance when the gravitational wave signal went through was equal to that times 4 kilometers, which works out to about 10 to the minus 18 meters, which is 1 over 1,000th the size of a proton. And so what you had was 1.4 billion years ago, these black holes collide, producing a huge gravitational wave signal. But when that spreads out so much during the 1.4 billion years, by the time it reaches Earth, all it does is it changes the distance. This 4 kilometers is now 4 kilometers minus 1,000th the width of a proton. And so it's absolutely incredible that they were able to build a device, an interferometer that was accurate enough to detect such a tiny change in distance and to actually get the signal separated out from all the other possible, the noisy things from trucks driving by and all that, and match it to the signal at the other detector. So it's one of the most amazing pieces of science and engineering that has happened in your lifetime and in my lifetime, I would say. And so I wanted to tell you that to end the class. And so that's it. And I hope you enjoyed the videos. You can go back and watch them. I'll probably make them available. And it's been great teaching you this term. Thank you.